Start at the very beginning. A very good place to start. All right, so when we begin, we started with limits. This is the beginning of the birth of calculus. All right, calculus did not exist without the development of a limit, and Sir Isaac Newton was the guy, okay, who comes up with that. All right, so we got to define what it was to have a limit. There are limits that approach from what two sides? The left and the right. All right, so to have a limit, you have to prove that whatever is approaching from the left of f of x is equal to whatever is approaching from the right of f of x. All right, so that's the definition of a limit. The hardest part of this was notation and was making sure that you had your equal signs and that you had the limit and that you had your arrows going the right direction, okay? Could something have a limit but still have an open hole? Yes, okay. The cruciality, okay, the fact that an open hole would be important comes into play with continuity, okay? And so then we bridged the gap or made that leap for continuity. So continuity required not only the existence of the left and the right, but it also had to have the existence of a closed point, and that the function value at a needed to be the same as the limit value from the left and the right. And that's that point that often gets lost when if it says justify that it is continuous. You got to specifically say that it is a closed point and that the closed point actually fills the hole. You'll be asked to just evaluate some different kinds of discontinuities. So we have removable discontinuities. Okay, so let's just draw a quick graph. Draw any graph you want. It doesn't matter to me what your graph looks like, but a removable discontinuity of some kind. Okay, now a removable discontinuity has that open hole. You could also have a replacement value existing somewhere else, but it doesn't have to be the case. But if that hole is not filled, those are different kinds of graphs you could have. Okay, an analytical look at that would be that L, which is the limit value, does not equal to f of a. Okay, so you show L, the left and the right are equal, and f of a does exist. It's just the fact that the two things weren't equal to each other. Okay, so you show the existence of an L and the existence of an f and a. The problem is that they're just not equal to each other. This frequently happens with an f of x that has a denominator. Okay, so you might have something like, here's an example, x minus 2, x plus 2, and the denominator has an x minus 2. When you have a removable factor, the factor that's reducible, that produces a removable discontinuity. Okay, it's the kind of discontinuity, if you can see that, oh yeah, I've got factors. So you always check factors and see if factors will reduce or not. If the factors reduce, they produce a removable discontinuity. If the factors don't reduce, that's a different kind of discontinuity. Does anybody remember what that one is? That would be, an infinite or an asymptotic. Okay, so if it reduces, it produces a hole. If it doesn't reduce, it produces an asymptote. That would be a boundary line. All right, a jump discontinuity. Jump discontinuity is when you've got something from the right completely not equal to something from the left. Okay, an analytical way to prove that or to state that would be to say that the limit as x approached a from the left was not equal to the limit as x approached a from the right. That you can't even get limits to agree. So if you can't get limits to agree, then you for sure don't have continuity. If you can get limits to agree, but you can't get the function value to agree, you still have a discontinuity. These are most often piecewise functions. So you'll see something like this, okay, where the piecewise graph might be x squared plus 2 as long as x was less than 0, and then it might be x squared minus 1 as long as x was greater than or equal to 0. And then you could check the left and check the right and show that the two do not meet each other, are not equal. That's a jump. What's another word for jump? We called it a different name sometimes. Gap. Very good. Okay. Also known as, so if you want to add that, AKA gap. Okay. You can also call it a gap. All right. The last one is an infinite discontinuity. That would be where you have the existence of an asymptote that forces the sides to infinity. So you could have both sides going in the same direction. They're both going towards infinity, but it's still discontinuous because it will never be joined together. And then the analytical version of that is that the limit from either the left or the right of f of x would be equal to either plus or minus infinity. So if either side equaled infinity of either kind, then you have an asymptotic, so that was another name for it, aka asymptotic discontinuity, and that was another word for it. And an f of x for that would be a denominator that did not reduce. So you could have something like x squared minus 4x plus 7 divided by x minus 2. And even if you tried to factor that, it's not reducible. And so since we have all real numbers where x doesn't equal 2, because 2 would cause us a problem, that's going to force the discontinuity. The questions from this unit on the AP exam are few and far between, but it does form the foundation of what we're doing. Any questions so far? All right. So then the way you would be asked about this could be either with a function, or it could be off of a graph. So here's an example of how you would check a piecewise function. Is it continuous? So what three things do you have to check? Okay, to and from. So the left and the right. Okay, and then you also have to explicitly state the value that's equal to. So we will be checking three things in order to justify this. We'll be checking the limit as x approaches 2 from the left of g of x. We'll also do 2 from the right of g of x. And then we will do g of 2 itself. So there's a 3-point process to check all three things. When you justify, you have to be clear about your notations, or you have to write it out in English. So either have really good mathematical notation, or be prepared to write a sentence in English if you feel like your notation's not great. But you don't have to do more than what's necessary. What's necessary is the bare minimum here. I've got my notation written down, then followed by an equal sign that would come after that. And then I can drop 2 in. So I'd have the sign of negative pi halves. And that would be a trig value you'd be expected to know. Okay, the sign of negative pi halves is -1. And then for the second value, we would check 2 squared minus 6 times 2 plus 7. So 4 minus 12 plus 7. So also equal to -1. And because of the equality of the equal sign, or the inequality here, because I have the less than or equal to, I have the fact that g of -2 is indeed equal to -1 because it is equal to. That bar will include it. So all three things. And so your conclusion, when you write a justification, you would say g of x is continuous because, and there has to be a because reason. And your because reason would include the equality of all three things. So you could say because the left-hand limit equals the right-hand limit, which equals g of 2, and they all equal the value of -1. So all of those things are equal. Now, you couldn't just use the abbreviation LHL like I did here. without having properly written it somewhere else. It needs to be properly be written somewhere. You can use it in your abbreviation if you have it noted somewhere else, okay? So be careful about that. They're going to look for you to at least once have written it in the right way. Another way you'd be asked about this question is to analyze a graph. Which of the above statements is false? So this would be a multiple choice question. So we're going from one show your work and then one multiple choice. So they're asking you, can you read a graph? The first one is asking if the left and the right hand limits equal each other at 3. What would you say about that?
It's true.
Okay, true. The second one is asking, the implication is, since 6 doesn't have a plus or minus on it, what is the implication? That they already do match. So you got to make sure that that is true. Okay, do the left and right hand limits match at 6? Okay, are they equal to the function value at 6? Okay, so because that is a closed circle, we've got that also true. All right, and then the next question, does the limit exist at 5? No. Okay, the implication here, without the plus or minus, it means that the left and right have to both match that value. So there's a false value. Okay, now that doesn't mean that that's the only false value. Okay, you should always check the fourth one as well. This one says that the right hand limit and the left hand limits are not equal at at -1. Is that true or false? Okay, it's true. But you could have more than one false option, and then your multiple choice answers would be like A and B, or A, B, and C, or they give you all the different iterations of that. All right, so we'll wrap up at, yeah.
I was looking on the example one. Would you like to write that as a continuous at x equals 2? Just to make sure, because if it wasn't.
Oh, right. They're asking us, yes, continuous at x equals 2. That'd be good to include. Yeah, Chloe?
So you're saying that with the multiple choice that if you did multiple multiple.
It could be. So say they use Roman numerals. They do that a lot. Like this would be Roman numeral 1, 2, 3, and then 4. And then option A would be 1 and 2, or something like that. Or so they give you different combinations. That way they force you to check all of them and not just stop when you get to one you think. Okay. So every medic unit ends with a few tips for the AP exam. For this unit, it's watch your notation. Okay, and then the second one is to be sure to justify fully. With all 3 conditions, or with all 3 requirements. All of a sudden my Apple Pencil's not working funny. All right, any other questions on Medic Unit 1? This was chapter 1.